Okay, and off we go. So last time we were talking about doing integrals in spherical coordinates, and a couple more examples. These last examples, I mean, they're fully worked out in the notes, and I encourage you to take a look at that. I'm just going to hit some what I consider to be key highlights of these examples. So in particular, let's think about for this domain here. Whoops, I wanted to be in highlighter mode. For this domain here, let's think about the range of values of theta. So, again, it's all about the picture and it's all about the geometry. And you have to think about how these theta slices look. A theta slice looks about like this. It's going to be a disk like that. By the way, if you have trouble seeing that, a pretty good 3D visual aid is to, get yourself a sack of oranges and a knife. Be careful with the knife, please. But you can just kind of think, and you can just take some actual cuts of the orange, right, and see what those cross sections look like, and they look kind of like this, right? Okay, now what's the starting and ending values? The key observation to make here is that this ball is entirely on the positive y side of the xz plane. If you go over to sort of the negative y side of the xz plane, there's nothing over there, right? Not a thing. And so, in fact, then what we have is that this first slice, the very first slice, the smallest value of theta that actually hits anything, is there at theta equals 0. Right, and then now, let's see here. Let me get rid of the I don't need this anymore. But as theta increases, it kind of goes around, and it's going to have significant slices all the way around over until where I get to that kind of far side of the xz plane, you might say. And the slices will be getting smaller and smaller as you kind of swing all the way over to that. But that's where it ends. And again, beyond that, you find yourself on the wrong side of the xz plane again. And so again, there's nothing over there. So pi then is your upper bound for theta. Does that make sense to everybody? Notice how the picture is how we resolve that, right? And it's not that it can't be done to make a case algebraically, but it's that it's a hard thing. It's a very difficult argument to make without a good picture. Okay. All right. So other details, y'all can follow those through, but that's the important point of this example. The next example I want to talk about, this will be the last one. This solid here, this is a weird looking solid. We've got, you'll notice first off, this ball here, which is this thing here. And then notice what we have here. This is a greater than or equal, not a less than or equal. So what that says is we're only looking at points that are outside of this ball. In other words, throw away anything inside of that ball. And so we're going to take this red bite out of that green initial ball. And I like to think of this as that I've got a scoop of ice cream, and then I take my ice cream scoop and then kind of take a round ice cream scoop chunk out of my existing scoop of ice cream. Something along those lines. Again, visual aids, right? It's a good excuse to buy some ice cream. So that gives you a hard thing to draw is the problem. The actual picture then is something kind of like that, but this really doesn't tell the story, right? I mean, because after all, there isn't actually a corner there. There's a kind of a sort of a lip, kind of something kind of like this down at the bottom there. Right? And if I were going to shade this in, how would I shade it in? And it's tempting to say, well, then you just kind of shade in the whole thing like this. But the problem is, looking in this general vicinity, yeah, there's solid in there. Simple story, right? But if I ask, well, what's going on here? What's going on at that point? Well, geometric appeal again, but I get solid, but then as I continue to look through in that direction, I get into where the scoop was taken out. So I go through some ice cream, and then I get into air, and then as I continue on, I get into the back part of the ice cream. So it's a hard picture to draw. I feel like this picture that I have here kind of doesn't tell the whole story, and it's a hard picture to draw. Right? All right. So how are we going to make sense out of this if we are having trouble even making a picture? And if I can't make a picture of the solid, how am I going to make a picture of the cross sections? So here's the idea. I think this is really useful, really clever. The idea is don't try to visualize the solid itself. Try to visualize these kind of components that go into making it up. So for example, if I take a theta slice, such as in purple here, of that green ball, nothing to it. That's an easy concept, right? That purple slice of this green ball is just a kind of a half disc. No problem. Let's draw that. Here it is. Here's that theta plane, and here is the half disc that is the slice of that solid ball. Okay, now what else have I got? Well, there's also this blue thing down here. Okay, well, again, it's just a ball. Nothing to it. The purple cross section of that blue ball is just another half disc. It's this blue half disc down here. So now, with all of this in mind, let's re-ask the question. What I'm interested in is what's inside of the green, but outside of the blue. And then I want to look at what's inside the purple cross-section plane. It's very hard to visualize. But if I just look at this picture, what's inside of the green and outside of the blue? There's no problem. It's already a two-dimensional picture. And it's pretty straightforward to see that it's this, what I'm shading in yellow there, which is a little hard to see, I suppose. But it's that thing right there. That makes sense? So I think it's a lot easier to draw the cross sections and then figure out how they intersect, as opposed to trying to visualize this very challenging way that they intersect and then take cross sections of that. That's much harder. I think this is quite a bit easier. So nice little trick. The rest of this example is pretty familiar stuff that we've talked about. So for example, you can talk about the phi bounds, and here's what the phi slices look like. Right? You can think about first and last, and the first phi slice is sort of clearly there at 0. The last phi slice is right at that point, right? Sort of the tip of the claw, as it were. And that point you can understand in a couple of different ways, and I encourage looking for the sort of the easy way out. And the easy way out here is to recognize that this is another equilateral triangle deal. And that being an equilateral triangle tells me that this angle, that value of phi, is pi over 3. Everybody happy? Okay. And other details that are a lot like examples we've already done. Okay, so that does it for spherical coordinates. Now we're going to move on now and talk about symmetry theorems. This is some really cool stuff. Underappreciated, underrepresented, in my opinion, in most multivariable calculus textbooks. I think this is a really powerful result. I used it tremendously when I was an undergraduate physics major. There was just, oh my gosh, so many integrals that I was able to just wave a magic wand at and just cite this symmetry theorem, and the whole thing just disappears. It's totally awesome. So let me first talk about what this theorem says. I'm going to start with the single variable version. Here's the theorem. If you have an integral and if your integrand is odd, odd, meaning that when you reflect the input, you get a minus sign on the output. That's an old concept from single variable calculus. Now, furthermore, if your domain is symmetric. Now, symmetric means, I'm going to say kind of exactly what you would sort of hope it means. Symmetric means, now I've written it down in kind of a precise way here, but I don't think this really is the easiest way to think about it. Symmetric just means that if you reflect it over the origin, that it doesn't change. So negative A to positive A, for example. If you reflect that interval, it's still negative A to positive A. Right? Okay. So big theorem, if your integrand is odd, if your domain is symmetric, then your integral is just 0. Drop the pen, walk away. Game over. We didn't have to integrate anything. Which is great because integrals are hard, right? I mean, this is really convenient, right? Now, how often does this come up in single variable calculus? Okay, I don't know, whatever. That's not really the point. My point is that it does come up a lot when you're doing multiple integrals. And so let me skip over some of this stuff. I'll come back to that in a minute. And let me talk about the two-dimensional version of these ideas. Totally analogous ideas. Oh, whoa, what happened there? Okay, here we go. Okay, so the first concept we need to talk about is the idea of reflection over a line. And reflection, I'm going to say it means exactly what you think it means. It's kind of like this. If you want to get precise about it, given a point x, the reflection is the point that makes this vector perpendicularly bisected by the line. Who cares? The point is it means exactly what you think it means, right? That's the easy way to think about it. Okay. So when you have a reflection, we can define what we mean by odd symmetry. What we mean by odd symmetry is that when you plug in a reflection, that needs to give rise to a 0 to the value of the function. That's exactly the same, I'll say, well, anyway, exactly analogous to the idea of odd symmetry that we talked about in the single variable case. And likewise, what do I mean by a symmetric domain? And again, this is, but let's not worry about stating this rigorously. You can write it like this if you'd like. But symmetry means that when you flip it over the line, it doesn't change. Right? It is its own reflection. Right? So, again, easier just to talk about it geometrically and, hand it. Okay. All right. So, why do we care about this? Well, we care about these ideas because of the following awesome theorem, which I have invoked countless times. And here it is. If you're looking at an integral, and if your integrand is odd in that sense, and furthermore, if your domain is symmetric in that sense, your integral is 0, and again, drop the pen, walk away. So, big win. There's such a huge win here. Think about your alternative. If you didn't have this symmetry theorem to just snap your fingers with, you'd have to slice up that domain. You'd have to worry about bounds. Then you'd have to do the inside integral, which involves an anti-differentiation, which can be a bummer, at the end of which you'd have to do another anti-differentiation. Again, maybe it'll work out, maybe it'll be okay, but it can be a real bummer, right? So this bypasses all of that, and the answer is just, boop, 0. It's fantastic. Super, super convenient. Now, bad news. So what you might call a delicate theorem. It's got to be just so. Both of the conditions have to hold. This is a common stumbling point for students. A lot of students will see a domain on their integral. The domain is usually what you're visually seeing when you're thinking about your problem. And they see a symmetry in the domain, right? And get excited about the opportunity to use the symmetry theorem, but they forget to check the integrand. That integrand's got to be odd. And, 1 out of 2 is, not good enough. It's got to, if that integrand is not odd, there's no symmetry argument to be made. And furthermore, very likely the answer isn't even 0, although, of course, that really isn't the point. Again, reminder, you've heard me say it a million times. It's not about the answer, it's about the reasoning. Right? So if the function's not odd, you cannot make a symmetry argument. Okay, yeah? Mm-hmm.
Can L be any line?
Yeah, you get to pick any line you want. Yeah, knock yourself out. Sometimes one or the other of these conditions could be satisfied by multiple lines. But this gets to the second thing I wanted to warn you all about. It does have to be the same line for both conditions, right? So it might be that you've got a bunch of options for lines that would make one work, and maybe a bunch of options for lines that would make 2 work, but you have to find a line that make both of them work. Yeah, absolutely. And by the way, it could be that there's multiple lines that make both of them work, in which case you still only have to find one. And you take your pick as long as the line you pick makes both conditions work. Okay, are we good? All righty. So let's talk about why this works, and then we'll start doing them. Why does this work? Well, let's go back to single variable. The single variable theorem. Here it is. We've got a symmetric domain, which means we're looking sort of from negative A to A, like this. And what's nice about that is that means that when I slice up this interval, I can pair up these terms in the Riemann sum. And so, for example, there's this term, and then there's also what you might call this term. Right? Now, what can I say about those two terms? Well, they have the same widths, delta x, and because the function is odd, I know that the value of the function at the one point and the value of the function at the other point are negatives of each other. Right? Is everybody with me? So that means I've got this equation down here, and with that settled, that tells me that this term, which is one of the terms in my Riemann sum, and this term, which is a different term in my Riemann sum, those are negatives of each other, and because they're negatives of each other, they cancel in the summation. And they have all paired up, and so everybody cancels with their sort of buddy term, and nothing's left, integral 0. Everybody happy with that? I think this is to me, the most sort of intuitively satisfying, the most visually satisfying point of view. Now, there's another point of view you can take, and that is you can do a substitution. Specifically, you can plug in x equals negative u, and if you plug in x equals negative u and just literally just do a substitution, then it just works out that this integral is its own negative. What you end up with, and what could possibly equal to its own negative? Well, only 0. So, real nice little argument. You don't need to worry about going through this argument. It's just I put this argument in here so that you'll know why I waited until this section, the section on change of variables, to talk about this, is because this substitution is just a single variable change of variables. And so it's literally a change of variables. So likewise, you can do a two-dimensional change of variables to prove this two-dimensional version of the theorem. And we just use the reflection itself as our change of variables function. Now again, you can walk through those details if you'd like. It's morally equivalent to the single variable substitution. But again, that's just why we're doing it here in this section, and you don't need to actually worry about this algebra unless you're curious. I think the better way, the more visually satisfying way to understand our 2D odd symmetry theorem is what I've got here. Which again, this term in the Riemann sum and that term in the Riemann sum, again, kind of pair them up by which is a reflection of what. Whoopsie. They have the same area. Right? If I look at the values of the function, well, because it's odd, we get this minus sign here. Right? Odd functions, the value of the function at the reflected point is the negative of the value of the function at the original point. And with that minus sign, if you look at this term in the summation, and then you look at this term in the summation, they're negatives of each other, and so they cancel. So I find this one more sort of intuitively satisfying for my own money. Everybody on board? Yeah.
So how do you write the reflection function?
Oh yeah, so that's a constant pestering problem. Yeah, it depends on the details of the circumstance. The short answer is going to be you have to draw a picture geometrically of what that reflection looks like geometrically, literally where it's taking which points to what points, and then let the picture guide you in terms of how you write down the formula. We'll see a couple of examples. Yeah, right. Yes?
How do you prove something's odd over a line?
Yeah, totally. We're going to do one of those as well. The short answer is that we're going to write down exactly the formula for reflection, just like he was asking about. We're going to then plug that into our function, and then we're going to confirm that it is the negative of the original value. Yeah, just straight out of the definition. Yeah. Okay. All right, so let's get our hands dirty. Okay, so let's do it like this. Okay, so question. There it is. We have a region bounded by blah, blah, blah. We want to compute an integral over that region. We've computed integrals before. You could look at this and think, I guess I'll just brute force this. But wow, what a nightmare this would be, right? Look at the integrand. Nasty, right? It's not that I can't integrate it. It's that I really don't want to, right? And by the way, that doesn't even tell the whole story, because we're going to have an outside integral to compute as well, and we know that whatever weirdness gets introduced as a result of the shape of this domain, and you can kind of see it coming, there's going to be some quartics that are going to get stuck in there, right? This weirdness is going to make the outside integral even worse. So again, it's not that I couldn't do it, but it's that I really don't want to. Okay. All right, so let's draw a picture of our domain. We'll start with this curve right here, y equals x squared minus x to the fourth, flashbacks to single variable calculus, and y'all hopefully remember how to draw these things. This one ends up looking kind of like this. I'm going to try to draw it reasonably. Close enough. This, of course, is an easy one. That's just a horizontal line, y equals -1. Let's say something like that. So our region, that which is bounded by those curves, is this thing right here, and I'm just going to make a hand-waving appeal. Symmetric over the y-axis. So here's the y-axis. I claim it's symmetric over that y-axis. Now, let's suppose you don't believe me, or let's suppose you're not convinced that you would have noticed that. Let me talk you through how you can see this for yourselves. Here's the formula for the reflection over that y-axis. Now let's talk about how to make that reflection formula. Well, if I have some point here, x comma y, here's a picture of how I compute its reflection, right? If I start at this point, the reflection is this point, and again, I'm just going to make a geometric appeal. When you do this, the y-coordinate doesn't change. And the x-coordinate of my new point is just going to be the negative of the original x-coordinate. You just kind of, again, you draw the reflection on the picture, and then you just interpret from the picture. Does that make sense? Yeah, okay. Yeah. Every example is different. By the way, we're going to do another one where there's a different geometric sort of picture we can make out of it. Yeah. Yeah.
Separate question.
Yeah.
So is there like a list of, like functions that you should know the shape of? Because the ease with which you drew the one in green, I couldn't do it.
Okay. There is a whole section in single variable calculus classes called curve plotting or something like that. So, how did I know this? I've done them a million times, right? And I kind of remember. But here's a way to think of it sort of intuitively. Let's think about what this looks like for small values of x. For small values of x squared is really small, and x to the fourth is microscopic, right? So for small values of x, this is morally x squared, and so that's why I kind of drew something sort of vaguely parabolic there. But now let's think about what this looks like for large values of x. For large values of x, x squared is really large, and x to the fourth is bonkers, right? And so this is going to be an upside down quartic, which is going to be kind of like that, right? So just sort of, the quick intuition, we basically talked through why it's kind of like that there and kind of like this there, and then I just kind of filled in the blanks, kind of roughly speaking. Is that satisfying? Yeah, something along those lines. Okay. All right. Okay, so we've got our formula for our reflection. I'm asserting that green curve is symmetric. How do we actually see algebraically that green curve is symmetric? And the big idea is I'm going to take my formula for my reflection and I'm going to stick it into there, which makes it turn into this, which I can do a little bit of algebra with, which turns into this. And just notice that when you plug your reflection into this equation, same equation. So what that means is that this green curve is its own reflection, which means it's symmetric. Is that cool? All right. Okay. All right. So we've got a symmetric domain. I further claim that this function is odd. Now, golly, let's think about how to show this function is odd. There's a couple of different ways to think about this. I'm going to show you what I consider to be the easy one, and then I'll show you the careful one next. The easy way to see this is to say, okay, well, the way we compute oddness, or decide on the question of oddness, is we look at what happens when I plug in my reflection into my integrand, and then I just have to check and see, do I get, fingers crossed, do I get the negative of the original value of the function? Okay, so we're gonna see if that works. Okay. All right. So the easy way to do this is to just kind of literally do it. So again, we have this formula for our reflection. Reflection of xy is negative xy. Now, what would it mean to plug in this reflection into my original function? Well, notice where I would have normally plugged in an x, I'm plugging in a negative x. So this negative x makes that a negative x. What do you think? And then likewise, of course, here and there. Is that cool? Okay. All right, now that leaves us with a little bit of an algebra challenge to work through. Is not so bad in this case, right? Negative x, quantity cubed, is the negative of x cubed. Let's see here. The negative of x squared is just x squared. That negative kind of goes away. Now let's think about this negative of sine of negative x. Well, sine is an odd function. This minus here goes to the outside of the sine function, so we're going to have, in some sense, two negatives. That's going to make a positive here. Is that cool? All right. Happy conclusion is that if you look at this and compare with that, and keep in mind the goal is I want the value of the function at the reflection to be the negative of the original value of the function. Are these negatives of each other? And why, yes, they are, sure enough. And so this function's odd. Very happy. All right. Okay, now I'm going to show you the other way to do it, but before I do, let's go ahead and spike the football here. We were looking at this integral right here, and we showed the domain is symmetric. We showed the integrand is odd. Over the same line, integral is zero by symmetry. I didn't have to touch that nasty integrand, at least not from an anti-differentiation point of view. Okay. All right, so let's do the oddness the careful way. What's confusing about what I showed you here originally is that I was basically saying, hey, let's stick a negative x in where there's an x, and that kind of seems sort of wrong. Right? That's a confusion of variables, and I committed a little math crime there. If you can keep track of that in your mind, it's totally fine. Go ahead. It's as long as you write this down correctly, that's fine. Right? But if you don't like it, all you got to do is rewrite the formula for your function. So I'm going to literally rewrite my function. Let's see here. I'll do it in orange here. I'm going to represent this by describing f now being a function of s and t. Just because I can. Just to avoid the confusion of variables. So, okay, well, this is going to be now s cubed e to the power of t squared plus 1 minus t sine of s. Isn't that cool? The same function, but instead of writing it as a function of x and y, I'm writing it as a function of s and t. And now, when I say that I'm going to plug in, let's see here, I'm going to plug in this reflection. I'm going to plug that reflection, negative x comma y, I'm going to plug that into my function. Now I'm very literally and unambiguously, this minus x is my s. Now that's not a, I don't have to, just keep track of the minus sign and make sure to remember when you're talking about the input x or the output x. No, none of that confusion. F of negative x comma y, negative x is literally s. Y is literally t. And so everywhere I see the s, I put negative x. Let's see here. Did I copy this down wrong? Look at what I did. I'm sorry. I copied it down wrong. Shame on me. Nobody caught me either, though. This right here is also an s. Sorry about that. That had been an x. That's the first variable, right? So I'm sorry, I wrote that down wrong. This is s. There we go. So if negative x is s, then that becomes a negative x, and this, likewise, a negative x. So just rewrite your function. It avoids the confusion of variables, and now the plugging in is very literal. So take your pick. Okay, so now let me talk about how to make one of these arguments on an exam. Bunch of details. Let's want to clear up the the mess here before we go on. Here we go. Okay. So if you're going to make one of these arguments on an exam, and I encourage you to do so if the opportunity presents itself, because again, it's such a huge time saver, powerful stuff. By the way, let me talk about why I'm so enthusiastic about these theorems. In my undergraduate physics classes, I had to take a bunch of, right? Integrals everywhere, just tons and tons and tons of integrals. A lot of y'all are engineers. You're going to be seeing tons and tons of integrals as well. My estimate, I believe this is a conservative estimate, is that about 20% of the integrals that I saw, zero by symmetry. And if you think about the fact that I had to take 9 classes that were physics classes chock full of integrals, that means a full 1.8 courses worth of integrals. I got to wave my magic wand and make them just disappear. It's a tremendously powerful trick that will save you tons of effort in various circumstances. Okay, so that's why I'm excited about it. I hope you will use the symmetry theorems. But again, you do have to give me a complete symmetry argument, and a complete symmetry argument, I require 5 specific things that I think are non-obvious. So in particular, you're going to have to tell me what is the line of symmetry. Note I did in this explanation here. I wrote that's the y-axis. You're going to have to tell me what your formula is for your reflection, your explicit formula for the reflection. Right? Let's see here. You're going to have to give me an observation that the function is odd, a valid, correct observation that the function is odd. Right? You can't just assert it. Then furthermore, you also have to give me a proof of that. Now, it's just this algebra here, right? It's not that bad. It's just a matter of kind of, again, you plug in the reflection formula, do the algebra, and confirm that it is indeed the negative of what it's supposed to be. Right? I just need to see that algebra written out. Sometimes the function is what I'll call obviously odd. Even in those cases, I need to see the algebra, because sometimes obvious is not as obvious as you think it is. And by the way, it's a small requirement. If it's so easy, it's easy to write down. Right? So please always do give me that calculation showing that the function is odd. And then lastly, you need to observe correctly that your domain is symmetric. I need to see that assert. The fact that the domain is symmetric is a huge part of why this works. So you got to doff the cap to this fact. Now, what you're going to notice is conspicuously missing from my list here. You don't have to prove that the domain is symmetric, right? So I wrote this in here, this business that I'm crossing out in yellow. I wrote this just in case, maybe you're having trouble seeing it for yourselves and you needed persuasion from me as to why this domain is actually symmetric. On an exam, you don't need to do that. You have to assert that the domain is symmetric, and you have to be right about that. You don't have to explain it or prove it. Everybody on board? Okay. All right. Now, why do I require specifically these 5 things? This is also a story from my undergrad. When I was taking all these various physics classes, tons of tests, on multiple occasions, I found myself stressful situation, working as fast as I can, running out of time. Oh gosh, here's an integral I need to compute. 15 seconds left. I don't have time to work this out. Equals 0 by symmetry. Handed it in. Most of the time it didn't work. A couple times it did. Right? So, cool. I got credit for something that I didn't deserve credit for. Right? So now, being as I am aware of that particular loophole, right? I do need to, and as much as I preach about how this is not a class about answers, it's a class about reasoning, that's why I emphasize that I do need to see the reasoning. So please do make sure to give me these 5 things. Now that said, outside of this course, in your engineering or physics classes, right? And on your physics tests or engineering tests, as long as your instructor's okay with it, if you want to, throw up that Hail Mary pass in the last 10 seconds of your exam, good luck. I hope it works. But I do require the explanation. Okay, let's see another example. I'm sorry, I got ahead of myself. I do want to give you all a warning about something. This is a unfortunate, scary reality, and that is that symmetry arguments are dangerous. So please do be careful. Why do I say they're dangerous? They only work if everything works. Right? If any one of these fails, there is no symmetry argument to be made. Right? Now, if there is a valid symmetry argument, and if you give me 4 of the 5 conditions, but you forgot to observe that the domain was symmetric, but it was symmetric, you just forgot to say so, well, then you get 4/5 of the points, right? So, no problem there. But the dangerous thing is if you forget to check whether the domain is symmetric, and it isn't, then what you have is 4/5 of 4/5 of the way toward a roadblock, which is not a solution. So you've gone all the way down that highway, and the solution's over here. You made a long way down that highway toward nothing, right? And it's just not progress, right? So when you choose to put your eggs in the basket of a symmetry argument, you got to make sure, be really sure that actually is a valid argument. Because if it's not, then you got nothing. And it's very, very hard to justify any partial credit because, again, it's not progress toward a solution. So, like I say, beware and do be careful and double check everything just because of that danger. Okay, now real quick example. Let's look at this hypothetical student response to a certain question. The question is compute this integral. The student response is these 3 lines here. Student claims the domain is symmetric. It is. Student claims that function has odd symmetry. It does. Student claims that integral is equal to 0. It is 0. The student claims that this is 0 by symmetry, that there is a symmetry argument that is why they claim it's 0. True. Everything the student has written down is true. And it is 2/5 of what needs to get said, right? So the student has correctly observed that the domain is symmetric, and the student has correctly observed that the function has odd symmetry. The student didn't say a word about what the line of symmetry was. Here's the thing. The domain has 4 of them. I don't know which line you're talking about, right? It's importantly unclear whether you're claiming symmetry around the line y equals x or symmetry around the line x plus y equals 1 or around the line y equals a half, right? There's various different options there. Which one are you talking about? I don't know. It's very important gap in the reasoning. Likewise, no discussion of the reflection formula, no discussion of why the function is odd. Not at all obvious that this is odd. The fact that the exponents are odd doesn't do it. Right? It depends critically on what line are you reflecting over and what's the nature of that reflection. So this student gets 4 points out of 10. Right? So please don't make this mistake. Right? Give me the full argument. I'll give you the full points. Does that make sense to everybody? Okay. All right. Okay, another example. The main purpose of this example is to talk about a weird reflection. So let me go quickly through the rest of it. We have a domain bounded by certain points. It looks like this. I say that is geometrically clear that it is symmetric through this line. Right? Now again, geometric appeal. I'm not going to prove that. You can prove it if you want. This is the argument here, but you don't have to. You don't owe me any explanation. You just have to be right. Okay. How would I come up with a formula for this reflection? This is a tricky one. Given the line that we're looking at here, the formula for the reflection over that line, let's see here. Here it is. Pretty weird because this point goes over to there. Some people would say that, aren't I just taking the negative? Isn't that just the negative? No, it isn't, because look, that's what the reflection looks like over there. That's not the negative. Right? This is not obvious what this formula is. The best way to see this, I think, right, is to look at what I like to call the rectangular frame of the point xy. And what's nice about this little rectangular frame is that this horizontal part of it, if I reflect that horizontal part, this being as it is a 45-degree line, horizontal just turns into vertical. And likewise, vertical turns into horizontal. And so it's pretty immediately clear that that green frame turns into that blue frame. And then you can just look at this reflected point here. That point has those coordinates reading straight off of that little geometric picture. I want that expand. Okay, there we go. Everybody buy it? It's a nice little trick. I didn't think of this myself. Somebody showed this to me many years ago. But the little rectangular frame, easy to see how that behaves when you reflect over a 45-degree line. Now, this only works if it's a 45-degree line. Right? So there's different hacks for different lines, different kinds of lines. Right? This is what's useful in that case. Okay. All righty. Here's a landmine. Dangerous landmine. Looks easy. Got an innocent-looking little triangle. You'll notice quickly if you draw this triangle, it's symmetric. Right? Tempting. You look at your integrand here. Your integrand's y cubed. Ooh, hey, cool, right? Odd exponent. Looks like we got a symmetric domain, odd integrand. Tempting to say equals 0 by symmetry and drop the pen, walk out of the classroom. And that's wrong. And it's just because of, again, you gotta be careful with the details. The point is they are using different planes. This domain is symmetric only through the y-axis. Only. This integrand is symmetric only over the x-axis. There is no line that makes both the domain and the integrand appropriately symmetric. There is no symmetry argument. The integral isn't even 0. Check it out. This entire domain is above the x-axis. Y is never negative. This integral is positive. There's no symmetry argument that would make it 0. So on a question like this, if you anything you write down about a symmetry argument, it's just nonsense. It's got nothing to do with the integral at hand, right? So again, be very careful with that. Last thing I'll just say real quick, it really is exactly the same in 3 dimensions. We just reflect over planes instead of lines. All of the same ideas. Odd symmetry is the same. A 3-dimensional solid is symmetric if it is its own reflection. It's exactly the same. We get the exact same theorem. We get the exact same warnings. You have to check both conditions using the same plane. It's exactly the same. The example here, let's see, how much time do I have here? 0? Negative? Do I have negative time? Oh, I have 20 seconds. Okay. I'll say something really quickly. This example is a nice example of how sometimes you need to use the integrand to figure out what your plane of symmetry, or perhaps in other cases, would be. If I want this function to be odd, I mean, I see that 3 there, right? We kind of foot in the door. We know that's got to be it, right? So in particular then, that makes me think, right, this 3 makes me think I want a minus sign to show up on the Z. This minus sign paired with that 3 is going to give me the oddness that I need. Okay, this is wishful thinking. I can't just declare some formula that I like to be a reflection. Now I have to ask the nasty question, is there a plane through which this is actually the reflection? And a little bit of geometric thinking will persuade you, yes, the XY plane is a plane, reflection through which will give you that formula, which will give you this oddness, integral is equal to 0. All right, see y'all later. Have a good one.